So hello everyone again. So this is the welcome to the second part of the introductory video on CST project. So in the previous video, we discussed about the like the first two components in detail. We went through all the 7 components, and then we discussed in depth the first two components, the high-level language design and compiler. I have also shown you sample code, taking the OS as the sample code, how the design looks like, and also the compiler working of the compiler, like what is the output of the compiler. So in this video, we'll go through the last, uh, the next 5 parts. So as we saw, uh, the parts that we built. So this is the outcome of the compiler. So the next part would be converting this particular temporary code to 3 address code. So initially this part, okay, before even going to the translator part, let us see ISA design. So even before you convert the temporary code to assembly code, you must decide upon the assembly language. So uh, the ISA design is something similar to what you have done in your CO course, uh, or in the CO course or the examinations, where the questions would be something like design a simple ISA supporting these instructions. What is the format of the instruction? What is the size of the instruction? And what are the fields in the particular one in an instruction? So that's what you would have learned there. So it's the simple application of that here. So here you will use that knowledge. Also, you will refer to one particular ISA, which your team will be given ARM or RISC-V or MIPS. So you will be using these as base, and then build a ISA on top of that, similar to them, similar to whatever they have. So the goals are design an ISA. So you'll be given an ISA to refer to. Like I said, ours was ARM. So our ISA is based on ARM. And so I'll just show the uh, like the team's presentation, like what it looks like. So this was the final presentation of our machine language and assembler team's presentation. So this has the assembly language specifications. So before you decide on the assembly language, you must take care of these things. Registers, like how many registers do they have? We had 16 registers. So which means that uh, you require 4 bits to address a register. So if suppose you are writing code for an add instruction, so there should be some part of code, which is the operation code, like what kind of operation is it? Is it an data processing instruction or a branch instruction or a memory instruction? So the instructions are basically divided into 3. Like we added one more thing, which is interrupts, whether it's an interrupt instruction or something like that, which means you require 2 bits for that. So that's how you address the instructions. So once you decide upon the opcode, and then you decide upon the operation. So add will have some part, like you assign 4 bits to specify whether what kind of ALU operation it is, what kind of data processing operation it is. So you'll be able to address 16 different instructions, and then you'll provide 3 operands, 4 registers, or an immediate value, or something else like that. So you have to decide upon uh, how to divide that. So based on the register count and the whatever things that you want, you'll be deciding this. Uh, so and also constants, labels. So this is the part of assembler. So that's why they mentioned this. But the thing is like this: the register size is 32-bit. Of course, 32-bit registers. So the register, each register will store a 32-bit value, and there are 16 such registers. And register representation in assembly code would be something like R0 to R15. So R1, so you can have reserved registers. So that's also what we have to discuss with the OS team, and also the like the OS team, OS team, so that what are the registers that the OS requires for bookkeeping. So there may be few registers which cannot be used while translating because they are reserved for specific operations by the OS. Because there's a stack pointer. You can like stack pointer is local, you can use that. But there are some interrupt registers. So a register stored to specify what kind of interrupt it is. That will store an interrupt number, and then you'll go to the interrupt table, and then accordingly, whatever interrupt it is raised, the corresponding handling code will be executed. That particular part you cannot use for register allocation. You cannot use for normal instructions like A equal to B plus C. So you'll be given limited number of instructions, like what you see in MIPS. There are instructions that start with S0, S1, S2, I think 6, 7 registers. Those are used for this regular purpose. There are some registers for T, temporary registers. And there is a zero register, there is a return register that is used to store the return value. So there are specific registers which have specific roles. So accordingly, you divide the registers, what can be used for normal computation and what will be reserved. Accordingly, you will be using those registers when you generate the assembly code. And again, because there are 16 registers, you just need 4 bits to represent. And also the addressing mode. How are you going to address? So whatever address, the destination address that you want will be PC plus 4 into offset, which means that like if you are in the second instruction, each instruction size is 32 bits again. So the register size, the number of registers, the instruction size. So these are all different things. You may be always be visualizing them as same, but it need not be same. You might have learned 32, like the MIPS. There are 32 registers. Each register size is 32 bytes, 32 bits, and the instruction size is 30 bits. So 32. It doesn't have to be that way. It can be any way, whatever you wish for. But there are like there will be complications, like if you you cannot have 13 registers because it will be optimal to use 16 registers, because anything from 9 to 16 will take 4 bits. So why not use completely? Why not have as many registers as possible? That's what. So there are some decisions, but you'll understand like why it is that way. Why is it in the powers of 2, the register size? Why the something like that. So the offset is here. Like so, since each instruction size is 32 bits, the ISA is 32-bit architecture. So if you want, let's say you are in instruction 0, the current instruction is pointed at location 0, which means that the current instruction is 0th byte, first byte, second byte, and third byte. So so the addressing mode again, it's byte addressable. Like it should be byte addressable everywhere, anytime. They should also support word addressable. So we designed both of them. So there are 2 kinds of instructions. One is load word and one is just load, LD and LW. When you say load word, like load word and load byte, I think 2. So when you say load word, the load word instruction will fetch 4 bytes with the starting address given as input. So when I say LWR1 36, it means that whatever data that is in 36th byte, 37th byte, 38th byte, 39th byte, all these 4 will form 32 bits and then store it in R1. When we say load byte, you fetch only that particular byte and then keep it in registers, keep it in the register. So you have to have both word addressable and byte addressable. That's the flexibility that is needed when you keep working on like special characters like character array. So how do you do that? When you want to access one character, you definitely need load byte. If you don't have load byte, then you have to have some other way of fetching only that byte. So when you don't have load byte, what happens is that you will take load word and then mask it with some other register and then shift it and then get the required byte. You can either do that in an assembly level or you can do that in a processor level. So if you do it in a processor level, you'll be having, you'll have to, the processor becomes more complex. But if you do it in assembly level, the number of assembly instructions that gets, so every time you access a byte, it gets translated to 4 or 5 instructions instead of 1 instruction, because there is no load byte support in the architecture. You have to use load word and then mask it, shift, write back, like compute it, and then get the byte, correct byte, like the required byte. So according to that, you have to decide upon the instructions. So again, so there are these many kinds of instructions. The data processing, so R type, I type, and others are like data processing instructions. There are store, load, less than, or, and, division, multiplication, subtraction, addition. And there are branch instructions, jump, and there are jump instructions, and there are also memory instructions, load, store also. Okay, completely, yeah, okay. Load and store are combined here. But we have 3 types of instructions, 3 categories of instructions. So this is how a ISA design would look like. So these are conditional flags. So assembly, like ARM has this, we used ARM version 4 for reference. So ARM has these conditional flags. So these conditional flags are used, I think, for specific functions. But we didn't have that need. So conditional flags are used like this to execute a given instruction under some conditions. So if the previous computation resulted negative, only then would this instruction get executed. Or if the previous instruction is resulted in a 0 value, only then this one would execute. It's a conditional execution. So instead of having a jump and then executing it, they incorporated the decision of whether to execute that instruction or not within the instruction using this conditional flags. We can adapt that, or we can ignore that. We can like we just adapted that. So anyway, we don't require those 4 bits. Like we were full of bits. We had enough bits to complete our ISA. So we just left that as same as ARM. And there is opcode. I told opcode, right? So load memory instructions have 0, 1 opcode. Data processing has 0, 0. And then jump instructions 1, 0. 1, 1 is for interrupts, I think. So the I field will tell you whether it's an immediate value or not. I think that's what it is. So if it is I is 1, then the third operand is an immediate value. If I is 0, then the third operand is register value. And S is for shifting or something, I don't know. And this command is the operation. It is 0, 1, 0, 0, then it's an add instruction. For subtract, it would be something different. 5, I think. This is 4, right? Command 4, 5. So we can have 16 different operations and 3 operands. The last operand, the second operand, the second argument for the computation can either be an immediate value or a register. Here it's just register. And then load instruction. This is how load is encoded. Equal, the jump instruction is encoded like this: 24-bit offset. Like I said, right, whatever value that you have to jump, it's PC plus 4. So you are in 36 instruction, and the currently the PC would be pointing to 40th instruction. So if you have to jump to 44 instruction, you have to just add 4. Not so when you refer, you're currently referring to PC plus 4, not just PC. Remember that. I think you'll understand when you start designing and then writing code. If you go through the ARM code. So labels. So this is what typically this assembling thing will happen in a 2-pass manner, I think. Yes, that's not assembling. Yes, assembling will happen in 2-pass manner. So in the first pass, you'll just write jump end. So we saw the labels, right? For each function sub will have a label. So when you write the assembly code, you'll just write jump label 1. But that will not get translated. That will not get assembled directly. So you have to actually find the offset of the label 1. What instruction it is, assuming that the first instruction is something else. So that's the assembler part. So you'll have to find the offsets and then use that and then replace that particular word with the offset. So jump end. So it's 24th instruction is okay. The end label is 28, which means that so 24 plus 4, 28 plus 28 instruction is what you have to jump to. That's what. So the 24th byte, so by 24th, 24, 25, 26, 27, this particular 4 bytes is the jump instruction. So plus 4, which means 28, plus the offset 28. 56 instruction is 56, 57, 58, 59. These 4 bits is what you are referring to. That's what this instruction says. So you'll have to go through 2 passes. So in the first part, you will assemble whatever that doesn't have a label. And then once you get the complete list of instructions, and then you'll start assigning offsets to those labels. That's a 2-pass parsing. And all the constants also you have to keep like the 24-bit constant. So if you want to go up the instruction, you have to something the current instruction is somewhere like, let's say you're in 8th instruction, you can go to 6th instruction or 9th instruction depending on the offset value. If it is negative, you will be going previous instructions. If it is positive, you'll be going to next instruction, jumping to the next part. So when you try to assemble a value, so that's what I used hash. So jump hash 28 means what? The 28 value will be converted to, so this is a signed representation, right? 24-bit value will be a signed representation. So signed bit will be 0, and then the remaining value will be 28. If it is negative, the signed bit should be 1, and the remaining values should be like 24, like the 2's complement representation. So keep in mind that. So the assembling also is important. So since we're discussing ISA, so yes, this is the, so that's what the ISA is. So the book that we referred for the ISA, I have attached the thing also here, the book, the link for the book, and this is the PDF that I found online. You could also find Digital Design and Computer Architecture ARM edition. There's also MIPS edition. So both MIPS and ARM teams can use this. I don't know whether there is an RISC edition or not. So this is the appendix by ARM instructions. So you can see, you can refer. So this is the data processing instruction, looks something like this. So we have destination register, we have first register, we have command, immediate value, opcode, conditional flags, yes. And the final thing can either, if it is immediate instruction, then it's something like this, immediate value or register addressing or shift register addressing, something like this. So the command, so you saw it, add has 4. We just adapted that. Subtract has 2. Subtract command code is 2. There are 16 different commands like this. And then I is 0. I think arithmetic shift right, I is 0, and something, some logic like what does I stands for, S stands for, everything like that. Multiply instruction and memory instructions, memory load and store, load store instructions. So loading a value from immediate value or from register addressing or immediate addressing. So branch instructions. So branch instructions will have offset and forward offset. So what kind of branch instruction it is. So you can refer to this book, and these are the condition flags. NZCV, negative 0, something C and V, I don't remember. Overflow, something like that. I don't know. C is for, I don't remember exactly, but these are the conditional flags. We didn't use conditional flags part of this. So you can refer to this. You can also use here the assembly languages. You'll see the high level code, A equals to B plus C minus D, get assembled to this part. So that this is temporary code, and this is the assembly code. So this is how you translate ARM assembly code again. So you can refer to this book. This was the book that we referred for the entire process design and ISA. You can refer the same book. Read everything from start. Read from start. Common. So if you are not familiar with process design, like simple, like whatever you learned in digital systems course and digital systems lab, CO course, and again you'll be learning all this in CST course also. You'll be learning basic components, RAM, PC, counters, adders, everything. So go through this book, especially this architecture part, chapter microarchitecture. Microarchitecture is compulsory. Like, this is the entire chapter that you must you should read this entire chapter as many times as possible. But this has the design process of the processor. So this microarchitecture chapter actually explains this designing of a processor. So we did a multi-cycle processor. You will be doing a pipeline processor. So multi-cycle processor design is like this. So multi-cycle data path. So there are different components in processor: data, instruction, data memory, PC, register file. So what is the data path, everything. So everything is in this book. I'll come back to this book again when I start talking about process design. So that's what. So that's the ISA design part. So design on the make a decision on the ISA. So you can collectively design on that. It's not it doesn't belong to some group, assembler team, OS team. I think everyone, all the system members can start and keep decide this. It's a very good fun activity. I think it's a decision problem. I think everyone should get involved in that. And virtual machine translator. This is the next part. So whatever we got like is the virtual machine. There was no translator part. We use translator. So the original project had us to use virtual machine. So the original idea of what Sir Dr. Janaran envisioned is like this. We will be writing an OS capable of writing an OS in some high level language, some C or some Java, Python, and then we will make changes to the compiler and temporary code generation part so that we will translate that particular high level code to assembly code of whatever we got. So the ARM code so there was no design of ISA actually in the first place. What thought is that we will be already using the compilers that are available, and then get the assembly code and go through that assembly code, get a small down version of that assembly code, and then design a processor to execute that particular reduced version of the assembly code. I think you understood, right? So there was no concept of writing an OS in your own language. That's not there. Writing an OS in your own language is what thought to be like a difficult task. So even when we propose when we are going to write OS in our own language, it's much easier. Sir didn't approve of that initially. He was he didn't has confident. He didn't have confident like really that would be achievable. But we thought that would be much more easier. So, or what you can do is you can write the OS in C or C++. Again, you have to use our own tasks, your own libraries. You can't use printf, anything like that. Or you can use printf. Wait, I think it's OS specific. I think it would be very difficult for you to write. So in that scenario, you would require a virtual machine to execute a separate set of code, language instructions, which you design again. So there are two parts. So the task will become two parts. One where you will be translating using an outside compiler, which is available compiler, and then executing processor, and then you design a language whose compilation and everything will happen in the language that you chose, C or Java. So let's not go into that. That's a even more bigger task, and that's what was expected. So whatever you are seeing is like down the small version. So it's still the project is still big. Still, the goal of the project is still high. This is just a watered down version of the project. So for now, we'll be using our own language. It seems simpler. We have the complete control of the entire thing, and also it's much more a good experience also. Other than that, very difficult experience. This is much better. So this is why we don't use a virtual machine here. We use a translator. So we built a translator and convert the tree address code to machine language. not machine language, assembly code. Machine language is zeros and ones. Assembly code is what we should call this I what's it up. So here we have to think of register allocation. So the register allocation part, I think we did the best way of allocating registers. It's very inefficient and very basic. That you shouldn't go for it. And also function calls, how to handle function calls and usage of special registers. Everything will happen here in this translator. So translator is also very large. So I would say if we I think this might help for teams to get divided also. It shouldn't spoil, but the hierarchy of difficulty when we come to the entire project is like this. Processor design is at highest. I think processor design would be at the highest. The OS would come next. Even compared to OS, processor design is the highest one. The second one is for you, since you didn't use compiler. Design compiler part should be difficult. Compiler, translator, and assembler. One. So that's what was sort of talking about the translating part, right? So difficulty part. Yes, so compiler and translator would come next. System integration also is very difficult. I think the easiest parts would be high-level language design and also assembler maybe assembler. Last would go the high-level language design. So accordingly, you make sure that you put utmost effort on this. So this is not for division of teams, but rather for your own awareness, like what should you concentrate more on. So okay, again, I'll show a demo of the translator, how it works. Let me remove this comment. So let us go ahead and translate also. So you just call this function and then pass the file. Let me pass sample.cmp. Okay, so this is the translation part. So till now, this is what we saw, right? This is for the compilation part. And after this, what happens is that, so for convenience, I'm showing what each temporary code gets translated to. So T1 equals to A2 plus B. Load R8 with the location of A. Load R9 with the location of B. Add that and store the sum in R10. And store R10 in the location of T1. So R14D is the location where you will find the variable A. R14 is the stack pointer. 8 is the offset. So stack grows reverse, right? Stack, I think stack grows. So it keeps on getting less and less as stack keeps increasing. So from that stack pointer, you add 8, you'll have A. Stack pointer, you add 4, you get B, or it is I think it's reverse. B is 4 and A is like the same. Okay. So and then you add that and then you store it here, T1. So this translation one must do, like where do you allocate space for these variables in the stack? You have to grow the stack accordingly. So you have to grow the stack accordingly, and then function passing, you have to push the variables to stack, get the variables from stack, and then do that everything. So the return statement. So return may seem simple, but there are many things. You are loading the value, whatever value that you want to return, and you're storing back it to stack, and you're loading some other value. You're loading the stack pointer to R12, like the return address. I think this is the return address, and you're adding the return address. I don't know. I have to see like what's happening and exactly here. But this is what is R10 will have the final return address. We'll jump to that. So this is how translation happens. So this translation part is, I said, it's difficult. So again, whatever I was saying is that this translation is dumb. You see, every time T2 is referred, T2 is referred here on load immediate R8. I'm loading R8 with value 10 and then storing it back. But I'm again using R8 here. So there is one store. These two instructions, if you see, they are similar. You're storing the value in R8, this value, and then you're loading back to R8. It's an unnecessary task. Like, you understand, right? So efficient register allocation is not happening. You could eliminate these two instructions right away. You don't need that. Actually, so you don't have to allocate space for T2 entirely in the stack itself, because it is immediately used and it is never used again. T2 will never be used again, if I'm not wrong. So you could entirely remove this. The number of assembly instructions will get reduced by 2. That's speed up. Basically, how well you can allocate registers. If you know that R8 was having here somewhere and you want to use R8, so you have to somehow allocate the registers in such a way that you will minimize the number of loads and stores, like the register spilling, right? That's what I think that's the name that we use, register spilling. How do you spill register? And if there are 5 variables and there are 5 registers, it's easy for you to allocate each register to that. So by the start of the function, with the start of the basic block execution, you will have all those registers and then store back. We will not have load and stores in between. It will be just computation. So you can, this is what we did. It's a dumb way, like we independently, it's just a map. So you see any kind of instruction A equals to B, this is the standard assembly code that's going to generate it. That's the, I think we did very less of a job in terms of digital allocation assembly, like this translation part. So because of the lack of, I don't know, some, but still you should not do something like this. Try to find the more optimal way of reducing as many instructions as possible. Try to reduce the number of loads and stores. Try to improve the efficiency of the computer also. Just not the working of the computer, but the efficiency of the computer. You will realize this water computer that we built is inefficient. If you see the game of Snake, you may see at first the snake is moving very fast, but as the length of the snake grows, somehow you are able to grow the length of the snake because you are a good player, and then you didn't get loose anytime, and you got some snake size to 20 or 30 bits. But then you'll start that the snake will start, you'll see that the snake will start moving slower because the rendering is happening. So the larger the size of the snake, more the rendering, which means the more the code is executing. And since the number of instructions is very far more, it gets slowed down. The rendering slows down because there are large number of instructions that need to be executed. So the snake will ultimately keep slowing down. The game will become easier, the length growing, because the snake gets slower. It will not get speed up because the number of instructions is more. There is no efficient time, and also the processor running. I think the processor running is the processor clock cycle is maxed. We did as much as possible because we didn't, without a cache memory. I think that's the highest frequency that you could run the processor on without having any breakouts or wrong computations. We try to push that maximum as possible. And again, you can introduce cache to reduce this latencies. You can have this efficient translation. So that's the part. So translation, since again high level language 10% should go for both compiler part and the assembler, people should start working with translation part. Try to have a very efficient, like possible, whatever you can, efficient translation is what is required here. And this is what so finally we'll have these instructions. So you see, right? Each instruction will have 4 bytes. So 0th byte instruction is this, 4th byte instruction is this, 8th byte instruction is this. So if you see here, what is the first instruction? Store word SWI R12 R4 R12. So these 2 instructions is added extra because main function calling. So somebody has to, main calls all the functions, and those functions will call other functions, but who's going to call main? So these two lines is what is going to call main function. So this you don't see in the high level, you have to add a translator. So there are many things that the translation people team should also include in their code. So there are additional things that they have to do. So I request assembler and translation to go side by side. And so this is the code. This is how the translation happens. Now the next part is the assembler. So the assembler will assemble the code. We translate the assembly code to machine code. Follow the ISO specifications decided already. So again, I showed the slides, right? Those are the slides, and I showed even the things. What is this? Is how the ARM instructions looks like. ARM version 4 is what is used in this book. So according to these specifications, you can just assemble it. I think assembler part. I think there are many things assembler part here. If you see, although like -120, or what we say is there is any jump instruction. Jump label 1. So label 1 got translated to -120. So this part is basically should be done by assembler people. So they wrote here code. Although the code is in the translator file, but that's the job of assembler team. So in the first pass you will have this code. In the second pass, you will assign labels to this. So label 3 is nothing but the 38, 39, 40, 41st bytes. So label 3 here. So that's what. So label 3 will point to 38. No, not 38. So I think 38 is the 38 into 4, I think. No. What is 38? It shouldn't be 38. Okay, something I don't remember. Some debugging value got printed, but again, each instruction will have some label. Label 3 is 38. Yes, okay. 38th instruction. Label 3 is pointing to 38th instruction. Okay, this is 38. So you decided that 38th instruction is the what is labeled R14-4. We have R14-4. Let's see. Maybe 3, right? Is 38. It's the same thing. So you see, right? So 38th instruction. So you will assign each label with the instruction that it is pointing to. 38th instruction, 21st instruction, 8th instruction. So again, in the second pass, you'll again jump switch begin. This is not translated. So this is not replaced by any of these things because switch begin is not in the code. Switch begin is the part of the OS code, which will get appended in the next stage. So in that stage, this switch begin will be replaced by some code because switch begin is an OS code. So you understood that. So this is what the OS team, like every time you see. So this again one reference that OS team will not have their job only with the high level language. So you have to write the code for switch begin. I think not the code, but the location of switch begin will be translated in the next part only. Because this is a sample program, there is no switch begin in this. If there was switch begin, you would have got that, but there is no switch begin in this. OS.cnp has switch begin. So, and this switch begin is basically an interrupt handler. This code is interrupt handling code. So what happens is that whenever an interrupt is very half a second, I told, right? So then this will jump to the handler of that, the process switch handler, jumping to that code. And jump -4 is a special instruction. Jump -4 will go to an infinite loop. So when you encounter like I told, right, the offset is PC +4 plus offset is where you jump to. So currently you're in 20. 20 plus 4 is 24. 24 minus 4 is 20. So you'll be executing again 20. So the next instruction always will be the same instruction. So jump -4 will be like an infinite loop which you can't escape unless there is an interrupt. So when you say that the voice there are no process running, or you say that if the computer side, basically this is what will be happening. The processor will not stop working. It would just be in an infinite loop. or it would be just be in a loop checking for new interrupts. That's something like that. So this is the translation part. And the assembler part I told. So assembling, let me do the assembling also. I think assembling will not work because there is no switch begin. So how do I run the assembler? I think I should. Will give an error. Yes, it's giving an error. So let's just no, we don't. We'll just compile the OS itself. So 364744 instruction is JR10. This many instructions is what the OS got translated to. And this will be converted to zeros and ones. That zeros and ones you can see in here. So these what do you see? 9186. There are how many instructions? I think 9186. 4 more instructions. So you have so 9190. So this is the OS. Here 9191 OS. So this is the so this is the entire OS. The final OS is what this is what it looks like. Final OS. So this is what goes actually to the processor. So that's the assembler part. And the OS is develop a code that the user sees. So as I said, OS is nothing but the code that is going to finally run on the computer. So if you have multiple processors, you need a management system. So the program will develop itself to a much complex management system, OS operating system. And then depending on the needs, that grows. But for now here, you can tell that like the program that is going to finally run on the processor is the OS. If it is like the necessary requirements to call something a OS, I don't know it's whether specific or not, whether strict, but for now that's what the OS is. But you will soon find that all the capabilities of a normal OS, you have to bring that to your own program also, because that's what will be required when you run process. So you'll find yourself developing that small program, which you might not call OS right now, but will soon develop into a program on the level of OS. Now, the language that is designed, yes, again, I told you, right? We are doing a simpler version of the envisioned project. We'll be designing the OS in our own language, written in both CNP and assembly. So there are a few functions that have to be written in assembly, requires to introduce new inbuilt functions into the language. So underscore ASM, underscore ASM, underscore, you'll see this in C also. So what this does is whatever input that it gets, the ASM, it's a string that will be directly translated. So the job of underscore ASM underscore is that it will enable the user, like the programmer, the voice, whatever program developer, to write his code in assembly language, so that you don't have to go to the translator code and then make changes for OS. But since we are doing in one single pipeline, we have command over everything. You could make that ASM much more what we call that, variable or flexible enough for you to go to the translator part and then change that. So you can or you can introduce new functions such that the OS stream will be still writing code in assembly, but it need not go to the translator part and then append change there. Instead, they will call something like this ASM, and then you start writing in brackets add R1 or R3. That will directly get translated and appended. You can do that also. But the reason is that I have to have access for few variables whose location I don't know when I write in a high level language. I think you will understand. So When I write the code int I int j, what is the memory address of I and j? I don't know. What register will they be stored? I don't know. But once it gets translated, I will know where I and j are. Then I can write the required whatever intended well, things that I have to do with I and j. So that time I'll know, but in high level language I will not know. So that's why we use this flexible ASM function. So quick click into os.np again. Okay. So let me go step by step. I'll just go through the instruction. I didn't show you the translation code, I think. Translator part. Again, some 900 lines of code. So what translate? What it will do is it will just the global table. The global table is nothing but the symbol table. And then it will translate each function. So there are many functions in a global table, right? We saw there is some function and main function in. Translate each function. Compute label positions, print label positions, print the code, get the code, everything. So these are the functions. So you'll be translating a function. Init code. There is some code that is added before the main function or in the main function. So all this code, this is what is written by OS people. So this part, a code dot pushback, I think this part is done by the OS people because they couldn't do that in the high level language. So the initial code in the main function before the execution of main function will be here, something like this. And global type, complete global, these are helper functions. And translate function will translate a function and then we take each token and then if that is a call temporary code, let's say each temporary code t code. So the temporary code is a list of t codes. If the t code starts with call, then it's a function of parse instruction with tokens offset and this thing. Else parse instruction. Parse instruction is what parses each instruction, each t code for now. So what we see, if we see a colon at the end, then that's a label. You will see positions token 0 substring is equal to a code dot size. That is the number that you give. What is the what position is the label referring to? Which instruction? Like it's the second instruction, third instruction, which will be nothing but the size of the accumulated assembly code that will be assigned to the positions. So a label position. If it is if parse, if you go to parse, go to I wrote like this is a much functional way of writing a translator. So based on the type of the instruction, the corresponding function will be called along with the tokens. So when we say token, add R1, R2, R3, add R1, R2, R3. These four are the tokens. So I'll pass the tokens and we'll call the parse function call. So like this is a big switch statement. So this is how it is done. And each instruction parse ASM. So how is parse ASM? So based on the type of the again, what kind of ASM you want to switch, fork, load, fork, enter, store, fork, return, label, switch, enter, switch, return, process, return, enter, process, return, exit. So this all, I think, when you keep developing, this may seem trivial. You'll find that this is how you should do. You may find a better way, but this is what we did. Switch, return, so parsing of each instruction, switch, enter. So this entire code is OS. Who writes this? The OS people have to come and write this. Do this. Switch return. This is written by OS. Like me, like our team wrote this. Process return exit. Process return enter. And like switch contest. Everything is OS. Set fork. Fork enter. Fork return. Parse string. So parse string. How is the string parse? So parse memory instruction. How is out parse memory? Okay. Oh, this is malloc. I think parse memory is malloc. This is how malloc instruction is translated to. Parse return. A return instruction is translated something like this. I'm searching for a much simpler example for you to explain. Parse arithmetic, yes. So parse assignment. So how did an arithmetic instruction get parse? Parse assignment. A equals to B plus C. So simple. This is parse compute. parse assignment, load, store. Okay, this is compute. So add R10, R8, R9. Load R8 with token 2, load R9 with token 4. Add that two values depending on the operation. Add that and store the value in R10. And then store R10 in the destination variable, the destination location. So store function will take something like this and computes the byte location or the word location where it has to store that particular variable. So this is entirely software engineering. You use those principles, try to build a reusable code, don't try to repeat code, try to make it decoupling everything like that. And assembler, assembler is simple. It may say, because most of the assembler code, the position location is in translate code. That's why the size may be smaller, but assembler is also a very big task. So you require so again, this instruction is parsed like this, something like this. So what here the person did is that based on the type of instruction, you're setting these flags. Conditional flag, operation. If it is parse instruction, then the opcode is like this. Immediate value is 1. Load, store stuff. This something. Load, if instruction 00 equals to load, then it is 1 or it is 0. So you have this small helper functions that will assign these values. And what at last happens is that once you assign the opcodes, based on the wait one second, machine instructions. So again, you see, right? Based on the instruction, you will append conditional part plus operand part, immediate part, load, store stuff, plus branch stuff, plus load, plus operation, plus set ALU flags, R2, R1, R3. So you're just appending. What it does is that he takes an assembly code. He'll assign all the flags. So if it is a a jump instruction, then this immediate value will be 0. It will be an empty string. But only when it is an arithmetic value, maybe this immediate value will have non-empty string. So he's just appending everything one by one. So you'll be getting a 32 instruction. So he's asserting that this size is 32. If not, it fails. And then the machine instruction dot pushback final instruction. So final instruction size is 32, zeros and ones, string. That's it. So this is a big task, but because Manjunath, whoever built this assembler, they build in such a way that it works smooth. It seems simple. Made the task simple, but the task is not simple entirely. So OS, so quick. So that's what OS is. Okay, I was talking about OS. So the PID. So the OS ID is 1. So the process with the ID 1 is OS. The current process is PID. And then when loading the value of the current process to R3. So R3 now currently has so R3 is like a special register, at least in our design, where it stores the process ID of the current process that is running, which is 1. And the keyboard location is 76,000, which means that the keystrokes values will be stored in the memory location of 76,000. And initially, for printing purposes, the line is 0, the character is 0. So when you call print function, it gets automatically by default prints in 0th line, 0th character. We have malloc function. So for a buffer, this buffer is nothing but the reading buffer. So when you open a shell, you type something. You type a string. So and you press enter. So if the string length is 20, where do you store that string? Where do you store the commands that are typed by the user? You have to store them in a separate variable. That variable is buffer here, which got allocated a 40 bytes of space, which means that you can at max enter only 40 bytes. We assume that the user can also enter many things. There are many things the computer will fail to work when you exceed, like the buffer. When you start entering more than 40 characters, yeah, it will either handle that by clipping the entire string to just 40 characters or something. I don't know whether I wrote the handling case, error handling case for that or not. And the current buffer index, so where to store that buffer, 0th buffer, the index, like where to store the next character that is entered by the user. Currently it's 0. And the map start. Map start is the again I have to see this. Map start is the starting address of the characters. Like when you saw A, when you press A, you saw A in that computer, right? The video. So how do you know what to represent when you press A? So that code is we got again from internet. So I didn't mention that here, but you can write like 8x8 encoding for alphanumeric characters. You can call that. You can assume that that's what it is. So if you search that, you will have. So assume that an 8x8 grid array, that two-dimensional array, filled with all zeros. And if that is the space where you'll be representing your alphabets, what cells should be 1 and what cells should be 0, assuming that 0 is black and 1 is white. For A, it will be something. It will only those cells will be highlighted with 1, such that that particular thing is A. That's what A, right? So this encoding you can start writing. You can design your own font style. You can design your own fonts, like 8x8 or 9x9, 10x10, whatever. That's the resolution. So how what is the resolution that you intend of the font? The resolution itself, that's what it's called. So it's is it 8x8, is it 9x9, 10x10, 12x12? If you increase the number of, if you increase the grid size, you'll have finer A's. So the A curve will be much more finer than something like 8x8 or 4x4. So you design that and you can, that's a decision, like that's a design process. You just take a 8x8 grid, just flip like maybe currently color these what things you have to have, and then this information for both lowercase, uppercase symbols, special symbols, and these things. So for all these things, you could you can do on your own, design your own font, and then store this information starting from this map start instruction. So, but what we did is we used font 8x8.h. So this is Unicode. So this is an 8x8 again. 1, 2, 3, 4, 5, 6, 7, 8. We use 8x8. So to represent star, what is the, like, it's an 8x8, right? We can assume that as a character array of size 8. So 8 bits, 8 bits, 8 bits, like that, 8 size 8. So the first 8 bits value, or the first byte value is 00 for star. Next is 66 and 36. FF 3C hexadecimal, 0x. So this is the 8x8 matrix, the representation. If you want to print star, we got this directly from net. You can do that also. For all these symbols, we got this entire code for every symbol. We even have this tilde symbol, open, close, bracket, parenthesis. So you instead of designing it's a hectic task and also redundant task, you don't have to spend time on that. You can use this, and this thing will all be converted. If you see memgen, I think memorygen has this thing. I think OS machine code implies that. I think we did once, and then font data start and font data end. So this is what the code. Print char, font 88 basic, current char byte, we reverse it and then print it. So this is what we did. So this you can have that. We can, and then this will go into some part of the memory. It's not OS. This will go into some part of memory, and you'll keep on addressing that particular part of memory if you want to print some character. So the real use would be here, print char. There is no print char. Is that display? Yes, display. So you'll be using map star. So based on the ASCII value of the, or Unicode value or ASCII value of the character that you are printing, you'll go to that particular memory location and then print. This is a very nice logic designed by Manjunath. Actually, he helped me in writing this particular function, which may seem small, like just 10-20 lines code, but this has so much logic into it. So k into 40 lines, so 40 characters, 30 lines being into it. So we debug this function, I think, at least for 2 hours. We tried many things, and this we kept on coming. We keep on coming back to this particular function because it didn't work. So you print, I print a, I say I just call print a very small function, and then try whether the a is getting printed or not. It gets printed reverse manner. So which means that the a is mirrored, or the upper part of the A will not display. And if you try to display ABC, you will not see ABC. You will see something garbage. So the entire mistake was, everything was perfect. Like we thought some assembler, there is some mistake in assembler, the map. We tested everything and came back that the mistake was this only, this particular function. So it's going to be difficult for you to write this kind of functions. So that's why I require to as many people as possible to involve in other tasks. Maybe the assigned person may not be able to solve that, but the other person may have an idea, so we can help them. So try to do that. So getting a line from the user, string comparison function, print string, something like print strings, get string, getting a string. Getting a string is different from getting a line. Getting a line will stop when you press enter. Getting a string will stop when there is a space. Just like scanf, right? Scanf, if you scan, you'll be scanning until you see a space. But if you use get line, you'll get the entire line. The same thing. Get num. How do you scan a number from scan num? Reversing a string, printing a number, process return. These things. What happens when a process returns? So this is the entire logic that happens when a process returns. What happens when you fork a process? By forking a process, we mean we creating a process. Again, this fork, you don't have to confuse with the actual fork that we see in Linux. This fork will not have a parent process. It's an independent fork. When you fork a process, there is no parent-child relationship. That's an independent process. Every fork process is an independent process. There is no dependency in the process. There is nothing like returning of a process. When the child process completes execution, it doesn't return to the parent process. It just dies, and then parent process will separately go. I think there's a name for this kind of thing. You are delinking a process. You're removing the ownership of the process. You're removing the child-parent relationship. That's what is happening here. That's what default. There is no. That's what we decided to do. Create process. How do you create a process? How to switch processes? So there are two processes. A switch function will be what called an interrupt occurs. So in the processor, when an interrupt occurs, there will be an interrupt handler that will go and then see what kind of interrupt. So there will be a register allocated specifically to store the interrupt number. So is it a timer interrupt? Is it a key press interrupt? Is it what we call a integer overflow interrupt? So depending on the type of interrupt, the processor, the logic is in the processor, and it will write that particular number to some register, a specified register, and it will go to the interrupt handler. The interrupt handler will see the interrupt number, and based on that interrupt number, the corresponding function is called. So one of those interrupts is the clock interrupt, which is a process switch interrupt. So when that interrupt occurs, the processor will point to this function. So this function will not be called by any function. It will be directly called by processor. It's a system call, switch instruction. So this is what happens. The switch happens. Print a. I don't know what this function is. Print a. Okay, this is for demonstration purposes, or process scheduling purposes. Print a. This function continuously prints a. That's the job of this function. Continuously prints a. It prints 10 times, 10 A's, with some interval. So what is this? For j equal to 0, j, this is some dummy code. Just so that I will be lagging. So there will be time. So from one A to other A, between there is some time that exhausts. So just to simulate that behavior, or else you'll see all the A's printing very fast. I don't want that. I want so A to get printed, then some execution, and then again A to get printed, some execution A. I wanted that behavior. Basically, I'm simulating sleep here. So the sleep function that you see in Linux. So print B, print C, print D. So I use this to demonstrate that the process switching. So I'll fork all the 4 processes. I start. So there are OS, the 1 process, and this 4 processes. All the 5 will be running. There will be process switching happening. So you'll see some A's. After that, you'll see some B's and A's, B, C, D, which means that basically the switching is happening perfectly. A, B, C, D, A, B, C, D, A, B, C, D, something like that. So that I want to demonstrate that. So that's why I wrote these functions. And also there's a locks here. When you see, like, let's suppose print string will print something like this. It will, so I said, right, A. So the A character is an 8 cross 8 matrix. So print string will print the top 8 bits, and then the second 8 bits, third 8 bits, 4, 5, 6, 7, 8 bits. So the printing will happen like this. So first you will see the top 1 line of the A getting printed. If you slow down the processor very much, you can slow down. You can the clock speed you can adjust in processor design point. Slow down the clock and then observe how A is getting printed. The first line will get printed, and then the second line, and then the third line, and then the fourth line, and then fifth line. So it will happen, or you watch some slow-mo guys videos, like how when rendering happen. You watch a video from slow-mo guys. They filmed this how actually TV works, like how each pixel like glows and everything. You see that it will go in iterative manner from left to right, top layer, second, third. So when you switch in between, you will see the top part as A and the bottom part as B, because the top before even completing the printing of A, the process got switched and B came. So you'll see some part of A and some part of B getting printed. You don't want that. So which is why you use logs. So when A is acquiring log, even if B comes, it will do nothing, because A didn't complete this print string didn't return. Unless the print string function returns, the lock is held by whatever process that requested by. Only so mutual execution. You whatever you learned in OS, right? So display lock. Display lock is nothing but an integer. It's a value. So you'll be acquiring that. I think here print string function, print string or display. I don't know. Number. It's print string only. Unless the print string completes, the lock will not be released. So if the display lock is 1, what this is doing is it's going in an infinite loop. I equal dummy variable I equal to 0 is getting assigned, because we couldn't have empty open close parenthesis. That's what we did. That's a dumb version. So because it was to force if for the producer to write something instead of doing dummy value. So the code will not come here. It will get stuck here. That is because the display lock is 1. The acquired whatever function that call that gets locked, and then it assigns 1. So by default the display lock should be 0. But if so happen that you call print string and the display lock is 1, you get stuck. You don't print anything. You have exited this and came to this line 211. That means that display lock was 0. It became 0 by some other process. And then you acquire the lock. Do whatever you want and then release the lock. So this is a simple lock. So it may seem like something different in Linux, but at the basic level, this is what is happening. Display lock is something which prevents this kind of behavior. You may not know, we didn't know, like couldn't envision, like we couldn't fully understand the real need of a lock. But once we develop OS, we learned that okay, this is where locks will be useful. These are the problems that, because I saw half A's and half B's getting printed. Only then I introduced locks. I didn't introduce that before. So when you see half A's and half B's, sometimes you even see you get an A printed, and then on top of it you see a B printed, and the same thing, because the new line is incremented every time, right? No, but the character plus the column will get incremented. So the code got stopped exactly at 233, that it completed printing complete A, but it didn't increment the column, which means that the next letter should be printed right to that. It exactly stopped here, which means which is why the A got, because the character didn't increment, it's getting printed in the same space. It's overwriting whatever value that was previously written. So these things happen. So these are the things that you'll be doing in OS. So I'm going through quickly without much explanation, but you're getting there, yeah. print S, print B, print C, print D, Fibonacci number. So these are the demonstration programs of Fibonacci. So what is the process here? Like the process is nothing but a big function, right? It has main function, but here the process is nothing but a function. So Fibonacci is a process. Fibonacci is also a function. Just that the Fibonacci code is in terms of a process, but Fibonacci is a process here. That's what we choose. There are no separate files for process. You will see in the future work that I'll explain later, where you can have Fibonacci as a process, entirely different, not part of the OS. So Fibonacci, we thought of doing that, but that's a big work, and it will like the time didn't permit us to do that. So the reverse string is a function, the demonstration. Prime number, these are the example things that I showed. Partition. Partition, I don't know what is partition. This quick sort algorithm. So the partition is part of that. Sorting algorithm, insert the tree algorithm. Yes, we used binary tree. Binary tree, not binary tree, binary search tree. So in order traversal, pre-order traversal, post-order traversal, get key press, get random, a random function. So you see, right, how are random functions generated given a seed. So this is how random functions are generated based on a seed. So this is a simple function. So every time you see how come you get the same sequence of random numbers? Try to see this is how it is done. Set food. So this is snake game. Display game or display player, no player. Snake game. Parse command. So this is the shell. How will you parse command? You'll enter. We'll compare the command that is entered by the user. If it is clear, then we call the clear shell function or print string function. If it is ls, you print all the commands. If it is FIVO, you call corresponding. This is shell, the shell. So the shell will initially display welcome screen. Welcome screen, nothing but whatever you see hello world. I think if you see the video at start, whenever you boot the computer, you will see hello world. That is done by calling this function welcome screen. And then the shell comes. So this is simple code. You will be able to write this. It shouldn't be a problem. And process design, the part that's most difficult part. The OS part, if you are a good software engineer, you would have an OS part, but everyone is a good software engineer indeed. But processor design is not a good, like you don't have experience with designing a processor. You had OS lab, but no processor lab, which is why this would be difficult for you to write. So the processor design thing, I think I'll again takes a break. I think it's more than 1 hour again. So I'll wrap here and then I again come back again for the next part, process design part. Okay. So process design and system integration, and then it's final. That's it. I think the video will get completed. Thank you.